and off we go. So we're going to continue these slides, finish them up today. Variables assignment, math and strings, oh my. So we stopped, last time we talked about division, that was fun. We talked about some types that we already know, chars and strings, how to do fun stuff with them. And then, there's always two sounds, aren't there? Sound 1 is muted, sound 2 is supposed to be muted, but it's not. Confusing. There. And so we talked about a lot of types. Let me talk to you a little bit about types in general. How much can we fit somewhere? How much stuff can we fit inside of a type? I think I can make this slightly bigger. No, I can't. Never mind. And there's going to be a lot to do with powers of 2. So that's going to be fun. 1s and 0s. So let's get started. How much stuff can we put in a type? All right? So the first thing I want to say is the size of a type. That will make sense eventually. This entire slide I'm going to show you a second time after I tell you what all these words mean. But just read it for now. The size of a type has to do with how much information you can put in that type. So, for example, an int is, why is that so small? Do that. That's better. All right, so an int, for example, that is 4 bytes that an int takes up, if you know what that word means. I'm going to teach it to you later today. 4 bytes also means 32 bits, which is another word I'm going to teach you today. And taken together, in general, that means that your int type can hold numbers from -2 to the 31st power to positive 2 to the 31st power minus 1. That is the range of an int. You want to go bigger, you got to use a different type. Right? So that's all you can fit in an int, because 4 bytes is a finite amount of memory. All right? A char is a single byte, very small because there's not a lot of characters. A char can hold values between -128 and positive 127. All right? Doubles are weird. Doubles take up 8 bytes. They're big, twice as big as an int. And they hold numbers that can be giant or tiny. So like -1.7 to the 10 to the 308th power. So very large numbers. This is a very small number, I guess. To very large numbers, the opposite of that, with about 16 digits of precision, though. It like stores them in scientific notation. It only gets you 16 digits of actual precision. And the reason it's called double, by the way, is there's another type that holds decimal numbers called a float. It stands for floating point, and that is 4 bytes long, but we don't use that in this class. That's half the precision. So double was like, they made that because it's double the precision of a float, double the number of bytes, right? There are other integer types that hold whole numbers that we don't really use in this class. There's short, which is half the size of an int, so you can hold this much stuff. And then there's also not 1 long, but 2 longs. Long, that's a type, and it takes up double the amount of an int, but it holds whole numbers. So it holds 2 to the -2 to the 63 to positive 2 to the 63 minus 1, right? So that's a lot of words. And I don't assume that you know what the word byte or bit means, so let's talk about those. What in the world is a byte or a bit? To get there, I need to first teach you about number systems, just math. We need to go to math for a second and talk about just bases and base conversion, because there's something implicit going on when we do math as humans that we don't really think about. We need to think about it right now. All right? So let's talk about bases, binary, bits, and bytes, all these B words. So our numbers that we use as humans are in base 10. Have we heard that word before? Base 10. We've heard the word decimal before, right? Base 10 means decimal, all right? Our numbers are decimal. Another word for that is base 10. You can see the deca, like that prefix in the name, right? It's a Greek root or something. And the reason we use base 10 for our numbers is because people think it's because we have 10 fingers, and that's how we counted. So we end up with 10 digits. When you have a base 10 number, that means you're using 10 digits to build it. That's our number system. We have the digits 0 through 9 to work with for our numbers, and so that's 10 digits total. And so that's what it means to be in base 10. You have 10 digits to work with. You could have different bases. You could write numbers in base 5. That's a number system. You can write any number under the sun in base 5, and following this pattern, what digits do you get to use in base 5? you get 0, 1, you get 5 of them, 2, 3, 4. And you have to build your numbers using only these digits. It's kind of weird. Okay? So, and a valid base 5 number would look like 1, 2, 3. That works. That's totally fine. And so I'm going to write numbers in different bases now. And I'm going to use a subscript to tell you what base I'm considering. So this is 100 subscript 10 to mean 100, decimal number 10, 100 in base 10. That is absolutely not the same as 100 in base 5. It's going to end up being a smaller number because you have fewer digits to work with. This is the same bunches of symbols, but in the base, it's a real different number. All right, we think in terms of decimal, not in terms of base 5 usually, and so that's fun. Binary is base 2. So that means the only digits that you get to make your numbers with in binary are 0 and 1. And so that means, all right, your first, that 0 is 0 in binary, 1 is 1 in binary. And then I need to make the number 2 in binary. I've just run out of digits in my current place. I need to add a new place. So 1, 0, see that must be 2 in binary. That's all we get. So 1, 0 base 2 is equal to 2 base 10. The 2 decimal number that we know and love. Okay? So that's the kind of symbols that you're going to get used to now. So that's binary. That's bases in general. Are we good with that so far? We care most about binary numbers in this class and other powers of 2 bases. So we want to shorten some of the words that we're going to say a lot. So instead of saying binary digit, like a single digit of a binary number, some people took the B and the IT and they shoved them together and called it a bit. So binary digits are bits. And therefore, like 1011, for example, that's a binary number base 2. I haven't told you what it is yet, how to compute the decimal number equivalent, but this is a 4-bit number. We'll say that a lot. This is a 4-bit number. And so that's a bit, a single binary digit. A byte is 8 bits. It's anything in binary that's 8 bits long. So your smallest byte is all zeros, 8 zeros. 0, 0, 0, 0, 0, 0, 0, 0. And your largest byte value is 8 ones. 1, 1, 1, 1, 1, 1, 1, 1. Okay? So just some string of 8 bits is a byte. So like the 1, 0, 1, 0, 0, 1, 1. Whatever that is a byte value. Right? That takes up 1 byte of space because you got 8 bits that you need to use to store it. Okay? So maybe if you were living in the Simpsons world, you'd be working with base 8. They apparently have 8 fingers. Any questions about any of that? So that's a number systems, basis. All right? Lots of new terms. So this is 1011 base 2. I told you that 10 is 2, and then 11 would be 3. 100 would be 4. You could try counting that way, but there's a quicker way to convert. Let me show you that. All right, so let me show you how to convert from binary to decimal, and it has to do with expanding under powers of the base, and it follows a pattern that you already know that you learned in like elementary school or something. So do we remember how to break down? How we learned to break down like 1,234, that decimal number? We learned in school that was like, all right, that's 1,000 plus 200 plus 30 plus 4. Remember doing that? So that will help us convert from binary to decimal. Once we got a little bit older, we got in math class, we learned that this is the same as 1 times 10 cubed plus 2 times 10 squared plus 3 times 10 to the first plus 4 times, you can still do times 10 if you do it times 10 to the 0, right? That's 1. That's the secret. Where's the base appearing in that expansion? Do you see it? It's everywhere. Base, 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 base. And so you can do that same thing to convert from binary to decimal. Just your base is 2 now. You're going to do times 2 to the something. Okay? So usually you work from right to left. It's easier that way. So this is, this digit right here, that's the 2 to the zeros place. Okay? So this number, whatever it is, let's convert it. It's 0 times 2 to the 0 plus, all right, what's this one? It's 1 times 2 to the 1. That's the next place. 1 time, the power gets bigger. This is 0 times 2 squared. It's the 2 squareds place. 0, 2 squared plus 0 times 2 cubed plus 1 times 2 to the 4th. All right, same pattern, just a different base. And so this expands to, simplifies to 2 to the 4th plus 2 to the first, which is 2, 4, 8, 16, plus 2, which is 18 in decimal. All right, so that's your answer. That's how you would figure that out. So 10010 in binary is the number 18 in decimal. Does that make sense, that process? Any questions about that? So that's how you do it. I don't know. Here, let me show you the pattern. And I have a question for you to try. You don't have to write this down anywhere. I'll give you a couple minutes with the people sitting next to you. See if you can get the same answer together. All right? So please convert 1111, the largest 4-bit number, to decimal. What is that? What's that binary number in decimal? Take like 2 minutes to try that. And help your neighbors. $30 more seconds or so. Yay! All right, so let's talk about this. First of all, did we all do attendance? Am I about to mark anyone not here? Maybe I'll give you 1 more minute just in case you forgot. What else was I going to say before we talk about this? Oh yeah, our lab 0. In case you didn't see the due date on Canvas, it's going to be Friday. This Friday at 5 p.m. is when our labs are due. It's usually a week. That next Friday is usually when the lab's going to be due. If you didn't see that. Okay. Back to this. Any brave people want to share their answers? What'd you get? 15. Yeah, that is the right answer. So let's break that down. Good. So this is the 2 to the 0's place. 1 times 2 to the 0 plus 1 times 2 to the first plus, I think you get the idea, 1 times 2 squared. That's that one. Plus another 1 times 2 cubed. Remember that it starts at 2 to the 0's place. Just like this started at, this was the 1's place, right? 10 to the 0's place. Same pattern. Don't start at 1. So that's computer science-y already. We start at 0 for that. Math starts at 0. So this is 8 plus 4 plus 2 plus 1, which is 15. So good job. Once you get better at noticing patterns, you'll learn like this is, okay, that's just 1, 0, 0, 0, 0 minus 1. So, and that one's easier to convert, but you can just expand the whole thing and it'll work every time. All right, so that's how you go from a binary number to decimal. If you want to go the other way, it's harder. So maybe pay extra attention now. This is a bit more difficult to go the other way, to take a decimal number and compute what its binary equivalent is, or just any other base too. This works for any base, this process, this algorithm that I'm about to teach you for base conversion. We are going to need a new symbol, a new idea, to learn how to do this. So I'm going to use the percent sign because that's what we're going to use in C++ anyway. That performs what's called the remainder operation, right? In math, people call that the modulo or modulus operator as well, the modulo operation. So if you see this together, 10% sign 2, you pronounce that as 10 modulo 2 or 10 mod 2, I'll say for short. And it means, please divide 10 by 2 and tell me what the remainder is. Don't tell me the quotient, the answer. Tell me the remainder, right? So 10 mod 2, what is that? It's like, all right, divide 10 by 2. It goes in 5. You get 5 with remainder 0. Remember that from math class? And that's what the percent sign gives you. It gives you the remainder back. So 10 mod 2, its result is 0 because it's an even number. 11 mod 2 would have been 1. There's 1 left over. Okay? So that's the remainder operation, and that's going to help us do the conversion. All right? So just like breaking down a decimal number, there's going to be a similar pattern to what you've already seen before. Kind of. Let's do this for a decimal number first. Let's convert the decimal number to decimal by extracting its digits. All right? This is going to lead to an algorithm that works for any base. So the question is, how do you extract the digits from the decimal number 1, 2, 3, 4 base 10? And my hint is you can go backwards. There's a way to take that 1, 2, 3, 4 and extract the 4, regardless of what this number was. If it was like 9999, there's some similar thing. You could do the same thing, you get the 9. How do you get the rightmost digit of any decimal number? Is my first question. Does anybody see it? 1, 2, 3, 4. There's a remainder operation we could do. What could I divide 1, 2, 3, 4 by and end up with the 4, the rightmost digit, in a certain place? It's going to be the base. Because the result is 123. Well, it's really 123.4, right? But that's just remainder 4. See how if you do the remainder operation, 2, 3, 4, mod 10, because we're extracting the decimal digits of this decimal number, if you do mod 10, that will give you the rightmost digit. All right? And now that I know how to get the rightmost digit of a number, all I need to be able to do now, if I want to get all the digits of this number, is to be able to like do something to 1, 2, 3, 4 to chop off that 4 and give me 123. Because then, if I have 123, then I can get its rightmost digit and make it smaller and chop off the 3. So what do I do now? What could I do to chop off that 4? What process? What operation? Do you see it? How do I fill in these question marks? What can I do mathematically to chop off that 4 and make it 123? And this will work for any number. Yeah. So the remainder by what? That would give me the 4 again. If you do mod 10, that gives you 123.4, so 123 with 4 left over. That is going to give you the 4 again. But that's the right idea. You do want to divide, because look, where's the 123? It's the quotient. It's the part that isn't the remainder. You already chopped it off. That's the secret. So do divide by 10, but do integer division. That's going to get rid of that 0.4. That'll give you the 1, 2, 3. Does that make sense? That's going to make it smaller, and now you can do this all over again. Get the rightmost digit. 1, 2, 3 mod 10 gives me the 3. You get 12 remainder 3, right? And then chop off the 3 to make it smaller to get the next number that I want to get the rightmost digit of, because I'm trying to extract them all. 123 integer divided by 10 gives me 12. Now I work with 12. Extract its rightmost digit. 12 mod 10 goes in once with 2 left over. There's my 2. Chop off the 2. Integer division goes in once, right? And then let's extract the rightmost digit of the number 1. I know you think we're almost done. We're getting there. Extract the rightmost digit of 1. 1 mod 10. If you divide 1 by 10, it goes in 0 times with 1 left over, so there's my digit. And then I want to shift away the 1, extract it, chop it off. So I do 1 integer divide by 10. That's 0.1, so it's just 0. Right? And that's when the algorithm is done. Once you hit 0, there's no more digits left, and you have reached the end, and you have extracted all the digits. So the secret is every time you took a remainder operation, every time you did the modulus, you got a digit, and you got it in reverse order, right? So there's 1, 2, 3, 4. We just extracted all the digits of this number back to decimal. Any questions about that process? Because we just extracted the decimal digits of this number. I think you can imagine that if you did modulus by 2 and integer divide by 2 instead of 10, you start extracting binary digits. If you wanted to convert to base 5, you do mod by 5, something like that, all right? So I'll give you this example. Let's do this for something we already know. Let's convert 15 to binary. We know what the answer should be. Let's prove to ourselves that this process works. Repeatedly divide, take the modulus by the base we're converting to. So I want to extract the rightmost, not decimal digit of 15. I want to extract the rightmost binary digit, the rightmost bit of 15. So I'm going to do mod 2. And, all right, the answer is, well, it goes in 7 times with 1 left over. The easy way to do this is to notice that if it's odd, there's 1 left over, right? When you divide by 2. So there's my 1. That's my rightmost binary digit of this number, right? My rightmost bit. And now I want to chop off this 1 in binary mode from 15, which is going to be integer divide by 2. That gives me 7. And now I want to convert 7 to binary by extracting its rightmost bit. 15 mod 2, or sorry, 7 is what I'm working with now. 7 mod 2. It's also odd, so I get 1, as I should. That's the next rightmost digit. Now I want to chop off the 1 out of 7, so the 1 bit, though, not the 1 decimal digit. So I'm going to integer divide by 2. I get 3. Right, then I extract the rightmost digit of 3. 3 mod 2. Goes in once with 1 left over. Shift away that 1 out of the binary representation of 3. Integer divide by 2. I get 1.5, so just 1. And then finally, I have 1 to work with. How do I convert 1 to binary? Extract its rightmost bit by doing mod 2. It goes in 0 times with 1 left over, 1 remainder. And then shift away the 1, give me all the other digits that I need to extract by doing integer divide by 2. That leads me to 0. There were no more digits. And I'm done, all right? And then in reverse order, remember, that's key, you got the bits of the number. So it goes 1, every time you took a modulus operation, you got a new bit in reverse order. So 1, 1, 1, 1. Which is exactly what we expected. We got that before. So 15 in decimal converts to 1, 1, 1, 1 in binary. And that's our answer. Any questions about that process? That's how you do it. A bit more involved than the other one, that's for sure. But still makes enough sense, I hope. So there's the process. And now, your turn. Please convert 117. You don't have to write this down, just help your neighbors. I'll show you my answer later. Convert 117, that's a decimal number. It's always you're going from decimal to some other base. Convert 117 to base 5, all right? So follow the same pattern, but I want a base 5 number now. And I've told you how to go the other way. So once you have your answer base 5 number, can you check your answer? So give that a try, and we'll come back together in like another 2 minutes and talk about it. Maybe. We can try ourselves. But, alright, was that enough time to get an answer? At least something were we able to check it? Do we know how to check it? So, let me walk you through how I might do it. Alright, so 117 to base 5. First of all, base 5, what are your digits that you get to use in base 5? You get 0, 1, 2, 3, and 4. And so that makes sense. That should make sense because when you do mod 5, your remainder can never be bigger than 4. Right? The remainder after dividing by 5 is never 5 or more. It's always 4 or less. So that checks out. That's why I want to do that. Mod 5, integer divided by 5. So let's do that. 117. The first, I want the rightmost base 5 number of 117. So I'm going to do mod 5. And that gives me, what did we get? 2. Oh, I need to do that. I'll do that in a second. But I'm going to cheat and use Python. If this ever loads, there you go. 117 mod 5. 2, cool. There's 2. And then I want to shift away that 2 in the base 5 representation of 117. So I want to do integer divided by 5 to get the next base 5 number to get. And apparently, 20? 23? Yeah, it's 23. And then we're off to the races. Then we want to convert 23 to base 5. If I do mod 5, it goes in and 4 times gets you 20, right? And then 3 left over. Shift away that 3. That's the next rightmost digit. 23 divided by 5. That's 4 point something. That's 4. And then we want to convert 4 to base 5. Well, it's already there, but let's run the algorithm to completion. Let's get the rightmost base 5 digit of 4. Goes in 0 times with 4 left over. Shift away that 4. 4 integer divided by 5. Chopping off any decimal places. That gives me 0. We're done. And then, every time we did a modulus, we got a digit, and we got it in reverse order. So it's not 2, 3, 4. So this was the rightmost digit. It's 4, 3, 2. Okay? So that's 4, 3, 2, base 5 is our answer. And you can totally check this on a test, can't you? Because you can go the other way. How do you convert this back to decimal? Well, 2 times 5 to the 0's place, right? 5 to the 0 plus 3 times 5 to the 1's plus 4 times 5 to the 5 squares. This is the 1's place. This is the 5's place. This is the 25's place. It's funny to think about. So that's 4 times 25 is 100 plus 15 plus 2, which is, what do you know, 117 in decimal. That's how you can check yourself too. All right? Any questions about this question? Those are bases. We care most about base 2 right now, but they're all similar. Might as well teach them all. All right, back to programming stuff. So now, here's this table again. I think it makes more sense, I hope. Now you know why ints can store this much stuff. I haven't told you how to store negative numbers. That'll be much later in the class. But you now know how to compute how many things 32 bits of something can hold, right? 4 bytes make up an int. That's 32 bits total, 4 times 8. And so the smallest int would be what? 32 zeros. And the largest int would be 32 ones, and you totally know how to compute whatever that is now. 32 of them, right? And so you'll find a number very close to this, right? And then char, that's one byte. The largest is like 8 ones, 8 bits long. Doubles are stored in a very weird way. You're going to have to wait till CSCI 45 to learn how doubles are encoded and how they work with their numbers. But somehow they're storing in 8 bytes. That's 64 bits of information. And then shorts and longs, I think, make a bit more sense now too. Hopefully. Those are integral types. So, are we good to talk about some programming now? All right, the first thing I want to tell you is just something useful for you as the programmer. It's technically not necessary, but it's really helpful. You can make constants as variables in C++, and all you got to do is when you make a variable, you just say out in front of it, just put the word const. Oops. you put the word const, and that makes it a constant variable, which cannot be changed after it's initialized. That's useful for like values like pi that never change. You don't want to accidentally add 1 to pi, and this will make sure you never can if you make it a constant. So make constants as much as you possibly could. So let me make that in code for you. And then I think somebody wanted this last time, and I left a note for myself. So here, if you want this, here is the folder where I put all of my slides that I'm showing you. I'm going to give you a link to it. Boop. In Discord. You already have the slides because this is the same slides as before, but for the next time, like I'm going to add the next slides to this folder, and I'm going to share it, if it loads. People, yes, copy. So I'll put it in Discord, which will take another minute to load, but I think it's worth it. And so if you ever want my slides, just copy this now. It will take a second though, and then you'll be able to go, hopefully, you don't have to log in. Let's try it. This link. Are you kidding me? I want a public link. Well, good thing I tried it. There's only one button to copy the link though, so that's... Really? All right. I guess we all get Microsoft accounts as the school, but let's see if I have any. There's the options. Yeah. Anyone there. Anyone can view. You can download it. Apply. Much better. Copy. So now, if you're not logged in, cool. All right. The only thing that's going to be missing is the cool font that I use. You don't get that unless you have it yourself. Here's all that. Sorry to derail us for a second, but I think a few people wanted this, and so now you can just always go to this link. It'll have my slides. All right. There. Where were we? Constants. All right. So let's get on. Let's make a new folder for today. On the class or on my local Linux computer. Dun, dun, dun. CSCI 40. Overwrite stuff. And then what lecture are we? We're lecture 3. So let's make a new folder called Leco 3. Now we're finally ready. And I'll make a file called const.cpp. And so, very simple. Double pi equals 3.14, right? This is a value that you can change. Yeah? That can be like pi equals 3 now. You don't want that. Pi is a constant. And so you say const out in front to prevent that from ever happening. So pi is a const variable. You can't change it now. It's meant to be like a normal mathematical constant, and it will be a compiler error to even think about trying. All right, ++ const.cpp-const. And it's like assignment of read-only variable pi, which is exactly what we want to see. So it won't let this happen. All right. So can't do silly stuff. It won't even compile like this now. All right. So hopefully that makes enough sense. Try to use constants as much as possible to keep yourself from doing bad things. So check for you the program. All right. That's constants. Next, I want to talk about functions because I've said this word already. Main is a function. What is that? I'm going to show you how to use other people's functions now. All right? I'll show you how to make your own later. All you know now is how to make main. But there is a similar process. That'll be a few lectures from now. But let's talk about using other people's functions that have been written for you in like libraries and stuff. So here's the anatomy of a function call. When you use a function, it's like you're yelling at it, asking it to do something. So you're calling the functions. Hey function, please do this for me. Okay? So this is what it looks like to call a function. You say its name, and then in between parentheses, you put anything that it might want to use as you're calling it, and you comma separate those things. Those are called your arguments. Again, the metaphor is you're yelling at it. So you're arguing with it, and here are the things that you're giving the function to use. Okay? So for example, there's a few functions that we want to use. Let me read this text first, and then I'll show you some examples. So a function, it's just a piece of code that somebody else wrote. Maybe you wrote it one day. I'll teach you how to write your own. But it's something that you can call multiple times. It's just in a nice place. You can use it as much as you need to. It saves your life. Okay? It can take 0 or more things called arguments, and those arguments tell the function what to use as it's computing its answer. Right? So that's the idea. Functions, usually they give back a result, they give back an answer, and you can pretend that your entire function call is getting replaced with that answer. Okay, so here are some examples of functions. The first one is the rand function. That's an easy one. It takes no arguments. You just say rand. I'll show you where it lives in a second. You say rand, it takes no arguments, and every time you call it, it gives you a new random number, which is useful for making like a game or something. To be different every time. So maybe if you call rand right now, it'll give you back this number, but if you call rand again later, it'll give you back a different number. That's a function that gives back something. And then math functions are useful too. So like there's a POW function to compute one number to the power of another number. So you can't write this 2 to the 3.5. You can't write that in C++, right? You can't even do a superscript. So instead, you call the POW function. You call POW with 2 arguments. The first is the base, and then the second argument is the power you want to take that thing to. So you say POW 2, 3.5, and this is going to go off, call the POW function that some nice C++ people wrote for us, and it will be replaced with whatever that answer is. All right, that's that one. And then you got square root, SQRT for short. If you call that, that gives you the square root of a number, and obviously that's going to take 1 argument. What number do you want the square root of? Right? And so every time you call a function, if it gives back something, you can pretend that it's getting replaced. So you can call it like this, SQRT of 2.0, and just give that to cout. Right? This will get replaced with the answer, and then we're printing it immediately. So this will print to the screen. This will compute 1.41, blah, 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 and then it'll print them. All right? So that's what those look like. And let's see, do I want to show you any of that on this slide? I do not. So let's wait till the next one to actually go to code. So here, let me teach you some math functions that live in certain libraries. They live in 2 separate libraries. They're from the C language, so the libraries start with the word C. We're stealing them for C++ purposes. And so some functions live in the cstdlib library, stands for C standard library, and then some live in the C math library. That's the C mathematics library, right? It's just places where people have implemented things for us. So let's look at these libraries. You can just search Google for like C++ cstdlib or C++ C math, and it will take you to a nice website. The website is cplus.com. It's like C++ cstdlib. What is that? I think the first link is going to be that place, cplus.com, and it shows you this. All right. Oh, I can stop attendance now, definitely. I forgot about that. So here's the cstdlib library. If you include it, you get access to all these cool things. Sorry, it's a little small. You can go there on your own. It's got all these cool functions you can click on to learn more about, but there's rand. We can use that. And then some other cool ones too. Absolute value, abs, exists there. That's useful. What do I want to show you? So that's cstdlib. We'll use that for rand a lot of the time. And then you got C math. That's over here in the C library. That has all the normal math stuff you might want, like cosine, sine, blah, blah, blah. Exponents, we'll talk about those. POW, we'll talk about that. But yeah, I think this should be where square root lives too. Did I pass it already? Dun, dun, dun. There it is, square root. If you click on it, it shows you a little bit more about it. How to read this is square root is a function that takes a single argument that's a double, and it gives you back a double. The first thing is the type that it gives you back. And then it gives you a cute little example program too if you want to know how to use it. But that's how you click on these things and learn more about them. But this is what exists in the C math library. So let me make a new file and we'll do math stuff. Yeah.
That website is pretty much always.
Yeah, you're
There's no way you're gonna remember every single function that there is.
You're gonna be living in that website this semester. So I'm gonna include the CMath library, and now I got access to cool stuff. I can be like, all right, see out the result of computing the square root of 2.0, and this will be replaced with the answer, and it gets printed. Cool, there it is. And you can do more. Let's see. EXP is another useful one. That's the exponential function. It takes a double, gives you back a double. It computes e to the power of that thing that you give it. So if I want e itself, how do I compute e using the exp function? Well, I can just call exp with the argument 1. And that computes e to the first power, which is just e. Maybe I can save that in a constant for later if I need it. So that works. Exp of 1. And even though it takes a double, I can give it an int. It'll make it a double. And there's my e. Cool. What else do I want to show you? There are 2 useful functions to... there's a bunch of different ways to want to round a number. Let me just say it this way. There's the normal mathematical rounding, where like if it's 5 or more, you make it bigger, blah, blah, blah. There are also some other kinds of rounding that will be useful to you eventually. And those are... Where are they? There they are. Rounding and remainder functions. So seal and floor, it's a cute metaphor. So if you have... They both take a double and give you back an int. It does a certain kind of rounding. It gives you a double, but it chopped off places. If you take the number 2.15 and you give it to sealing, the seal function, it's kind of like throwing it at the ceiling until it sticks at the next higher number. Even if it's small, it goes to the next higher number. So that gives you 3, the next higher whole number. That's the sealing function. The floor function is the opposite. If you give floor to any number, it's going to shove it down to the floor until it hits the next lower whole number. So that'll give you back 2, right? That's how those work. If you give the number 2 to ceiling and floor, it's already a whole number. It's already where it needs to be. Won't go any higher or lower there, but that hopefully makes a little bit of sense. So see out ceiling of 2.15, that'll give me 3. And floor of 2.15 gives me 2. Next higher whole number, next lower whole number. 3 and 2, certain kinds of rounding. And so that means I could ask for the floor of 2.99, and it's still going to give me 2. It's the next smaller whole number. There's my 2 again. Right? The normal rounding is just called round. So that's useful. That's the mathematical rounding that we know and love. So if you give to round, the normal round function, where is that? Should be in the same section. It's just called round to nearest. So if you give 2.15 to round, you call it with that. That gives you the 2 because that's less than 5, right? Less than 0.5. But if you give 2.5 to round, that'll make 3. That's usually the rounding that you most often want, right? So technically, integer division is doing division and then floor. Secretly. That's what it means to chop off decimal places. All right, so that's the normal round function. Let me show you that for posterity. Round. And so if I do 2.15, that'll give me 2. If I do 2.5, then it goes up to 3. All right. And it's happy. Any questions about these? So these are functions. Somebody else wrote this. I think you can imagine how hard it is to calculate the square root of a number inside of a computer. I'm actually going to force you to write your own version of the square root function later in this class. But it's difficult. It's nice to just be able to have it made for you and just to call it and use it. Okay? Any questions about any of that? I think that's all I want to show you for CMath for now. Plenty of other functions. Play around with them. Next, I want to talk about random numbers. And that lives in the other library. That lives in C-std-lib, C standard library. That's where rand lives. Let's go back there. C-std-lib, rand. That's where I want to be. So we're going to call rand, and that gives you a random number, and it lives here. Click it. So it generates a random number, takes no arguments, gives you back a random integer. It returns a pseudo-random integral number in the range between 0 and whatever random max is. All right? So let me try and explain that. So when you call rand, it's going to give you a random number each time between the number 0 and some constant called rand max, which is just large, bigger than you'd want a random number. And that's the idea. All right? Just some large number. What it is. We can actually print out what is random max. What's the largest random number I could ever possibly get? Let me show you that. Rand.cpp. So this rand lives in C-std-lib, and every time I call it, gives me back a number randomly between 0 and rand max. And let's see what rand max is. It's just going to be some big number. Bigger than you'd ever want a random number. Cool, so that's a very large number. So every time you call rand, you're getting back a number between 0 and that. And so let's call rand. Cout rand. And let's call it a few times. That's a random number, that's a random number, that's a random number. Dun, dun, dun. So I'm printing out 3 random numbers. This is rand max first. So these are my 3 random numbers. Yay. And I can use those to make a game or something, make it be different every time. Place my enemies on the screen in a different place or something. So that's randomness. That's how it works. Gets you a giant number, usually. And if I run it again, it'll give me random numbers, some more. If I run it again, it'll give me random numbers, some more. Wait a second. Technically, it's possible, randomly, for it to be giving me the same random numbers 3 times. It's just improbable. These are the same random numbers. Something is going on. So let's talk about that. These are not true random numbers. These are pseudo-random numbers. They act like random numbers for our intents and purposes. But if you ask a mathematician, they're going to be like, no, this is fake. Here's the secret. The way that rand gives you a random number is it's essentially picking from a random sequence. All right, so it's like first time the sequence starts at 1, let's say, and then once you generate a random number using the number 1 as your special secret number as part of your randomness, then it uses that to generate the next number in the sequence. Like, all right, I'm going to use 1 to generate 42. I'm going to use that to generate a random number. And then I'll generate 85 or something. And then I'll generate 12. Blah, blah, blah. But the idea is there's a sequence of random numbers. You call it on this one, then it generates this one, then it generates this one, then it generates this one. Right? That's how rand works. And if you don't give it anything, like by default, it just starts with the same starting value of the sequence. So you're always going to get the same chain of random numbers unless you start off the sequence in a different spot. You give it a different number to start its randomness with. Right? And that's called seeding the random number generator, like you're planting a new random thing. Right? So if we seed this random number generator, it will produce a different sequence of random numbers each time the program runs. And so there is a function next to rand called srand that initializes it, that seeds the random number generator. What you do is you give it some number, and that'll start it off, and it will use that to generate its randomness. Okay? It's called seeding the random number generator. And so we'd like to seed our random number generator with a different value every time we run our program so that it's different random numbers every time. What's a good number that's different every time we run our program? The time. The time changes every time we run our program, right? So we just use that to seed our random number generator. That will give us more or less randomness. It's as random as we could expect. All right? It's pseudo-random, but it really acts random, I promise. You'd have to run it for trillions, even more than that, to see a pattern. But we're going to say this. There's a time function that lives in the ctime library that we call. If we call it with the number 0, it gives me back the current number of seconds since January 1st, 1970. That's just a weird convention, but that's a number. I can use that and give it to srand, and it'll be different every time I run the program. All right? That's called seeding the random number generator, and then it'll work. So before you call rand, you seed it. Otherwise, it'll be the same. So you say srand, and you give it the current time as a number. So that's time 0. So look at how I'm using function calls inside of function calls. Like this is going to be replaced with the current time, and then I'm calling srand with that. So seed the random number generator with the current time, which is fun. And now it's finally truly random. Yay, so here are my random numbers. If I wait a second to run it, I get new random numbers. And now it really is different every time. You really can make a game that acts different, right? Or whatever else you need to do with randomness. Run simulations, maybe. Any questions about that? So we seed our random number generator, and then we're off. Usually, you don't want a number between 0 and random max. You want a random number between like 1 and 100 or something like that, something normal. You want to make a guess the number game. And so, let me show you how to get a random number between some value and something else. Let's say that I want to get a random number between 1 and 100. Sorry, let's say 0 and 100. Let's start with that. How could I shrink down the call to rand, whatever it gives me back? It's giving me back a giant number between 0 and rand max. How can I make sure to shrink it down to be between like 0 and 100? Any thoughts? And keep it random? What can I do to it to shrink it down? Because there's going to be some big number. How can I shrink its range down and also keep that random number random, so I can't multiply it by 0 or something. That would not be random anymore. What could we do to shrink it down? Any thoughts? What's that? Seeding it just gives you a different random number each time. You're still, when you call it, I seeded it here, and I'm calling it, and I'm still getting usually giant numbers. So that's not going to give us the thing that we need yet. Rand does not take any arguments. So it doesn't expect anymore. It'll give you an error if you try. But yeah, some rand functions will take that range for you. That's a good thought. But this one does not. Here's the hint. It involves something we learned earlier today. If I take my number and I do modulus on it, that will shrink it down to be between 0 and whatever I put here, -1. So I should do 0 to 101, right? If you take some number and you divide it and get the remainder by 101, that will give you some number between 0 and 100. Does that make sense to us? You take a number and you do mod 10 on it, that gives you a number between 0 and 9. That would be the remainder after dividing by 10. So the remainder after dividing by 101 is some number between 0 and 100. And it's not forcing any numbers to certain spots. It's just kind of overlapping every time, right? It's wrapping around. It's keeping it nice and evenly distributed. So it's keeping it random. Modulus is your friend here. So if I want, here's a demo that I'll do. If I want to get a number between 1 and the user's choice, which I'll call n, how do I get that number? I'm going to call rand on, I'll do rand mod n. That will shrink that random number down to be between 0, 1, all the way to n minus 1. But I wanted a number between 1 and n. So what can I do to this number, whatever it is, to make it between 1 and n? Just add 1. Yeah, if I add 1 to whatever that is, that will give me a number within the range 1 to n. Good. So that's how you get a number between some starting number and what you care about. All right? Do mod by something, maybe add something at the end. All right, so let's do that. Get a random number between 1 and the user's choice. Let's have the user enter a number. What's the highest number you want? Cout. Enter a number. Call it n. Get it with cn. And then what's our job? Calculate a random number between 1 and n. So cout, call to rand. That gives me a giant number. That's random. Shrink it down to be between 0 and n minus 1 by doing mod n. and then take that and add 1 to it. Now it's between 1 and n. All right, that's how we put it within the proper range. And so, all right, I want a number between 1 and 100, let's say. And there it is. Now I get a random number of 56. And if I do it again, random number between 1 and 100, there's my 98. And so it's random every time, and it's within a range that we actually care about. Does that make sense? And so if you want a random binary number, between 1 and 2, please. There it is, 2. 2 again. There's the 1. But you can make this as big as you care, and it will give you a random number between 1 and that by doing this operation. Any questions about why that works? Why this process works? Here's a fun one. Let's output 3 random characters, because what are characters but number values? Back up to the table. The ASCII table doesn't use negative numbers, so let's do numbers between 0 and 127. How about that? All right. Let's make character values between 0 and 127. So char c1 equals call ran do mod 128, right? That'll give me a number back between 0 and 127. It's always 1 less than the modulus. C2, C3, do the same thing 3 times, and let's print them out and see if it's useful. Some of these characters are unprintable, though, so we'll see if we get any printable characters. C out, C1, next to C2, next to C3, and a new line. I don't know, 42. And so cool. What did I get? 1 printable character. I got a quote character, and the other 2 were unprintable. Or maybe 1 was a space. Oh, I got it. No, I'm printing out the new line at the end. If there were 2 new lines, it would have been a new line. Yeah. Dun, dun, dun. What was it? Now, here's my random number between... Oh, shoot. Yeah, you were right. Yeah. No, wait, this was my random from last time. This time, though, I think it worked. So here I got a new line, a dot, and then an unprintable character. That's fun. This is like... Ooh, these were all printable characters. Yay, exclamation point, backslash, and 2. The digit 2 character. How fun. And so this is like, I don't know, 21st century Ouija board or something. Random characters printed out. How fun. Any questions about that? What are they but numbers? Numbers in the ASCII table. Alright, if we're happy, let's talk about... Where was I? I was down here. That was everything I want to do on that slide. Let's talk about strings now. There's a lot of string operations, and these are different. There is, the string type lives in the string library, which is not part of the C library, it's C++ stuff. It's in other string. I can click on the string type. It's a special kind of type. It's called a class. That thing I did for the counter example. Remember that? I said the word class once. But this works differently. There are functions that act on individual strings, and the way that you use them looks a bit different. So here's the list of things you can do to the string type. You can be like, give me its size or length. Those give you back the same thing. Give me back a character. We already know how to do that. There is a find operation that searches for something inside of a string. That's useful. There's like replace, erase. So these are things that you would want to do to a string. It knows how. These are library functions, but not really functions. Let me show you some string operations. So let's make an example string. String, let's call it S, make it hold hello. So there's a string, and remember what it looks like inside of memory. It's just a bunch of characters. 1, 2, 3, 4, 5. So that's the H character, the E, L, L, O. And these live at indices 0, 1, 2, 3, and 4. Don't you forget that. And so there's a bunch of different operations that you could do on strings, but they're not like a function call. It looks a bit different. There's a dot involved. And so when there's a dot involved, it's like S is secretly its own argument. I don't know. It's like, hey, saying string S, tell me your size. It's like you're talking to the string. It's a bit different. This is called a method. This type of syntax with a dot and a variable first, those are called method calls. But you can think of them as function calls right now. These are methods. It's a method. We say it acts on that variable S. So it's like implicitly S is an argument. It's like S, do this thing to yourself, maybe. You can think of it that way. But I guess the easiest method on a string is get its size. And that just prints out how many characters. It gives you back how many characters are in that string, which is useful to know. So let's do that one first. Oops. I'll call this strings.cpp. And so I want to include the string library to access the string type and all of its operations. So let's make string s equals hello. And I can output that string size by running the s method. Hey s, how big are you? It's kind of how you think of it. It's acting on s. What's its size? It's got 5 characters. Cool. All right, well, that's one thing. Another useful thing on strings is you can use plus. Plus is overloaded for strings. It just adds those characters together. It combines the characters of 2 strings. There we go. And so if I have a second string somewhere, string, I don't know, s2 equals comma space world, world exclamation point, then I can make a bigger string with the plus. String s3 or I don't know, combo equals s plus s2. That builds up a bigger string that has hello and then comma space world too. Print that. I get my hello comma space world. Built up a bigger string with both of those characters just shoved right next to each other. That's useful. And then these other 3 are also fun. So that you've got find, replace, and subster. These actually take arguments. So if you do s.find, you give it a character, it will find the first occurrence of that character. You can also give it a string. It'll find that character or string inside of your bigger string s. Right? It will give back to you the index where that thing is found. Right? So if I want to know what is the index of the h character in my string hello, it's the 0th index, right? It's supposed to be 0, but find will tell me. Find the first h, please. So int index of h, I guess, equals s.find, look for the h character, right? And we can look for other characters too. So remember that s is what we're searching through because we're saying s.find. Finds the first h. Let's find, I don't know, let's find the first l. Just to show you that it gives you the first one. And then let's look for a character that doesn't exist. Index of z. Let's print all those out. So, cout. Index of the h character. And then let's just put these all in the same line of space. Index of the l character. And index of z character. And a new line. So where is it finding all these things? It'll give back indices if it finds it, but there's no z in the hello string. What's it going to say there? So it finds the h at index 0 of the string. It finds the first L, so that's index 0, 1, 2. And then anytime it doesn't find what you're looking for, it gives back a special index that never is possible to exist, a -1. So it gives you back -1 to indicate that there was no z. Couldn't find it. Right? So that's .find. Oops. There. That's .find. Gives back the first thing. There's a different, I think there's a find that's reversed. There's rfind, it finds you the last occurrence of something. And if you click on find, there's a way to have it like find one in the middle. So like if there's 3 L's, find the middle one. You can give it like a starting position to search for, and that can secretly take a second argument. But that's for you to look into if you care. What next? There is s.replace. What this does, there's a lot going on there. You can click on it too. There's that substitute replace. It takes, there's a bunch of different options, but it's going to take an index, a length, and then another string. It's very, very complicated to read the documentation for this one. Let me tell it to you in words at least. You say s.replace start len s2, and then you just put a semicolon. This one doesn't give anything back. It just does the thing for you. You don't expect it to give anything back. It's going to change s, though. It's going to replace pieces of it. So what this does is you say s.replace. it replaces this many characters. It replaces len characters from S, starting at index start. So it chops off len characters starting at some starting index, and then it replaces those characters with whatever's in the string S2. All right? So you give it an int, and a string. That's how replace works. So it's much easier to understand this with an example. So let's translate. Let's convert our hello string into Spanish hello. So let's convert S, or right now S holds hello. Let's convert it to hola. And then what does that mean? We need to replace a few of these things. We need to replace these last 4 characters, right? So how do you do it? S.replace. I want to chop off, starting at index 1, so 0, 1, take away the LO. So starting at index 1, take away 4 characters, and replace those 4 characters that you just chopped off with OLA. It doesn't have to be the same length. You don't have to give it 4 new characters. You can give it 3. It'll make it smaller. It's fine. So that's S.replace, and now it's changed S. You're meant to just call this on a line by itself. It does the thing. Doesn't give anything back. And then now if you use S some more, it's been changed. So remember, it used to be just hello. Now it's going to be hola. Is that enough to see everything? Yeah. There. So that's replacing. So replacing, starting at this index. These many characters, replace it with this. That's how you think of it. What else? You might need that one day. And then subster is also useful. Subster stands for substring, so take a smaller string out of the bigger string. And so that is starting at some index, take how many characters and make a new string. S.subster. So starting at index start, take len characters and give me a string back. That's that substring starting from there. So let me show you that. Again, makes more sense with an example. I don't know. Let's extract the string la from hola. So if S holds this, I want not index 0, not index 1, but I want index 2 and index 3. So starting index 2, because that's where the L is. So string la equals S.subster, starting at index, because it holds hola right now, starting at index 0, 1, 2, starting at index 2, take 2 characters. Starting at index 2, take 2 characters. That computes a new string that you can save somewhere. We'll give you that. It's a substring. It's a smaller string inside of the string. Those are some useful operations that you might want to do on string type things. And there's plenty more where that came from. Check that documentation page if you're interested. Any questions about that? All right, for my last trick of the day, I have a question for you guys. We've talked about types a lot now. So I would like you to just take a second to get into peer instruction groups, say hi to the people next to you, and please go to the Written Nice page, which I will clear out right now. And hopefully it will reload, and this will go away and be happy. But what I'd like you to do is answer this question together. One of you can be the typer if you'd like. But here's your question. What is the difference between if I were to say 1, 2, 3 in C++ versus me saying between quotes 1, 2, 3? Right? When these appear in C++ code, what's the difference between this and this? Write down as many differences as you can think of in the Written Nice page. All right? What's the difference? Think of it in terms of what you can do to them as well. That's a hint. So take a few minutes to write some stuff down. Another 2 minutes to ponder this. Let's see what we're thinking. I can try to mess with the TV. Yeah, those TVs, I don't know. They should just be getting a signal, and they're not. Yeah, maybe once the lecture is over, I can go and ask the IT people. They can come take a look. All right, that's my timer. I hope that was enough time to get a few things down, get our thoughts down. Press submit if you're feeling brave. Thank you to these people. Let's see here. In quotes is a string. Good. So yeah, types. So key difference. What is the type of these things? String versus integer. Good. 1, 2, 3 would be a string that can be output of the screen, while just 1, 2, 3 could be a value that you could do stuff to. I like that thought. You could output 1, 2, 3 though. It would still output 1, 2, 3 through to the screen though. There's a bit more there. Integers are used for math, whereas strings can be manipulated as text. That's a great answer. So good job, group 92. That's exactly the kind of thing that I want to see. Yeah. What can you do? You can do math stuff on 1, 2, 3. You can do string stuff on quotes 1, 2, 3. That's kind of what I'm looking for. So good job to you guys. I think you're getting the right idea. So let's write this down. All right. So 1, 2, 3 by itself, that's just a number. It's an int technically. What can you do to numbers? You can be like plus, minus, times, divide. You can give it to pow and square root. You do all this math stuff with it. It will not accept quotes 1, 2, 3, any of those things, right? Well, some of them will, and I'll talk about that in a second. But you can do number stuff with numbers. Quotes 1, 2, 3, that's a string. What can you do to it? You can also do plus with a string, which can get a little weird. I'll give you an example there. But what else? Like you can do your dot size, dot substr, dot at. We'll go to an index of a string. All that fun stuff. So, watch out. The moral of the story is watch out. If you have quotes 1, 2, 3 and quotes 4, 5, 6, the two strings, what happens if you give those to plus? You get the string 1, 2, 3, 4, 5, 6. That's what it means to add strings. That's not what you wanted most likely, yes? So make sure you're using the type that is most useful to you at the moment, right? So I think that's all that I wanted to say about that. Are there any questions about anything? Because that's my last slide of the day. So the rest of the time, there is no new lab that I'm releasing. Your lab, remember, is due this Friday. So, sorry, wrong class. It's due this Friday. I will release your next lab, lab 1, next class. So the rest of this time today is to work on whatever is already out, right? And ask questions.